quite the rainy day today. So, right, if I remember, I can find it. Okay. So, in the previous video, we talked about behavioral resonance, I believe, and damp behavior. Well, that behavior, though, if I didn't discuss this, it's just simple. It's just basically we have the femboy and then we force them to settle with a certain thing. So, or if we have a gender fluid person and well, they oscillate back and forth, what we do is we force them to settle, right? We tell them pick a side. We tell them to say or to pick. Want to be a guy? Want to be a female? Want to be none of them? That's it. And then they say, "Oh, I want to be a male." Sort of there. So instead of it keeping on oscillating, instead of it continually oscillating, so I'm gonna take a picture here. Okay, so that's our M by G by T axis. G, and then it's our T axis. Time, and then our preferred gender identity, M and F, and of course we have our origin O. And then so instead of it being like this, well, it's just going to continually, and that's a sign of T equals G as our function. Instead of it being like this, well, instead what we're gonna get is something like this. So I'm gonna erase this guy. And instead of that one, we're gonna get something like this. So yeah, actually this is damp behavior. But if we have something that's critically damp, there's a special condition called or a special case which is called critically damp. And we're talking about critically damp, that means our object is, or our pendulum or spring is, it's forced, or it exists inside something as viscous as honey. So it exists inside a medium that stops it almost right away. So instead of that slowly oscillating down to nothing, or oscillating back and forth, instead we have something like this. So it steadily goes like that, and then okay, yeah, that. Or if we start in our equilibrium position, or if we start with androgynous in nature or nothing, or it doesn't want to identify, and then it suddenly wants to be a male, and then we force a critical damping situation, it goes like this. And it's something along the lines of G equals E to the minus kx sine kx. Of course, plus some constant c. Wherein the c is probably just 0 in our case here. So I'm gonna do that more around it. Okay, like that. So that's what it's gonna look like. That's for critically damp. But that's not our focus for this lecture. This lecture, what we're going to do now is step away from spring and instead think of femboy as a pendulum. So something that swings back and forth. So let's start with the basics of what a pendulum is. So let's start with the basics of what a pendulum is. A pendulum is a line, rather, or something with a bob, or something attached to the end. So as you guys know from, I guess, clocks or something, like from clocks, that's a pendulum. Or is an example of a pendulum is what's used in clocks. The camera, oh god. So something like that's used in clocks. So it has a bob, or it has a line, or a rod, and then a bob, and then we have some equilibrium position over here. And then so the angle it makes, we'll call the angle that it makes with respect to this equilibrium position to be theta. Okay, theta degrees. It would be very convenient to express it like this in this angle over here. So it will be just use the shorter version. And then proportionally there's a weight, which we will call m. And then there is a proportional, velocity. Wait, let me just open the book for our book of reference. So, of course, again, if you have the book, turn your pages to page 177, chapter 10.5, the simple pendulum. So, yeah, we have some weight W, not M. W, not omega, W. Some weight like that. And then we have some force over here. And then this angle is not some direct quantity, but it's a quantity expressed as a function of time. There. So theta here is actually theta is a function of time. Okay? So every step in time corresponds to an angle of this. So as time goes forward, with this setup over here, our bob and our pendulum itself swings this direction according to it. But if we say push it, going this direction, I had a haircut, so don't mind my haircut. If we push it this direction anyway, push it this direction, and then we proportionally get our own vector to be pointed in this direction, of course, as time steps forward, our pendulum is going to move that way, and then eventually fall down here, or stop at some point there because of air resistance, and then fall back down, and then continue swinging back and forth, and then eventually it stops. And according to physics, basic physics, the period or the time it takes to swing back and forth does not change. Okay? Or the total time it takes for it to swing back and forth before it stops swinging at all because of air resistance does not change. Unless you change the angle, of course, of where you drop it from. Okay, so let's set up the differential equation for this setup. Okay, so we have a rod that's suspended C units from the ground. So say C. Suspended by one end so that it can swing freely in the vertical plane. Let a weight B, a bob, which we will call the bob, this B, of W pounds be attached to the free end of the rod. And let, actually this is C over here. C is the length of the rod. And then so with respect to the horizontal, we have some angle theta. And we know that according to your basic algebra, or rather your basic pre-calculus, we know that this sector over here, or rather the area of the sector, or this slice here, is S. Well, let's call it S. Or have its measure be S, is equal to let's see. S is equal to C theta. Where theta is the angle over here, and then C, of course, is the length of our bob. And then we get our area for the sector. Okay, so yeah. Our theta here expressed in radians is our angular displacement from the horizontal. So from the place where we attach the pendulum from. And then, so the tangential component of the force W is W sine theta. So this bar over here, or this vector over here, or this vector over here, is expressed via W, the weight of the bob, equals W sine theta. And a quick gut check is that, notice if we try to create if we think of this as a vector, and then theta is sort of our reference point, we can do some angle chasing and then prove that indeed this theta over here is the same as this theta over here, for this alpha. So if we make some perpendicular plane to this, to the reference point, or the point where, or plane where we attach our pendulum for, we can do a little angle chasing and prove that this theta is actually equal to this alpha over here. And then so our force, that or our vector is basically just the dot product of this vector over here with respect to the horizontal. Okay. Okay, this is also W sine theta. If of course our bob is moving this way. Okay, then neglecting the weight of the rod and using S equals C theta as a measure of arc length from the vertical position, we can conclude S equals C theta. From there, we can conclude that minus W sine theta, or the negative vector component, is equal to W over G d squared S dt squared double dot S. Yeah. Where double dot S. Here we go with ink again. Where double dot S dot S is equal to d squared S over dt squared. You guys get to see that. Okay. So since our C over here does not change, of course the length of a rod doesn't change, and we know this relation S equals C theta, this equation over here, this minus W sine theta equals W over G S double S dot, becomes double theta double dot plus G over C sine theta equals 0. So you guys can still see that? Yeah. So theta double dot plus GC sine theta equals 0. And now we may notice here that theta is its own function. It's a function of t. And and then we're putting a function inside another function, so it's a bit difficult. And actually, the book states that to solve something like this requires something called an elliptic integral, which is an advanced integral that's non-elementary. But in this course, we're dealing with elementary cases. So the neat fact is that for small thetas, or for very small angles, sine theta is actually equal to theta. So a neat fact about this, about that. Did I pick the wrong? Okay, so our neat fact, not need for it to not. Markers. So our neat fact is that for small theta, sine theta is equal to theta. And this is actually part of the joke, which is called the fundamental theorem of engineering, is that engineers like to believe that this holds for all theta. But the thing is, what we mathematicians want to emphasize is that it only works for very small theta, for thetas that are such as 0.0000005 radians, or 0.000000000000001 radians. this sort of holds. So sine theta approximates theta for very small theta. I need to emphasize it only works for small theta. And if we assume that theta here is a small quantity, we can actually simplify this, simplify our equation a while ago, and make it into, we can make our equation instead into theta double dot plus beta squared theta equals 0. Where beta squared is equal to W over G. Yep. So we don't have that sign. We don't have that sign holding the theta hostage. And now we can solve this properly with separation of variables and all that. Yeah. And we also need to say that, again, we need to take note that theta must be small. In fact, it needs to be, it needs to be small. I'll assume with the book that the absolute value of theta, so assume the absolute value of theta is less than 0.3 radians. If you want to convert it to degrees, just multiply it by the reciprocal of pi over 180. So that would be 0.3 by 180 over pi degrees for this 0.3 radians. Okay. My sweat dropped a little bit. Okay. So now, you guys can probably guess that this involves something like sine. Or the solution to this involves something like sine. Yeah. Because of course we have sine here, we have a function over here, we have another function over here. So yeah, in fact, I believe the solution is something like sine of beta squared plus c. I believe, or k. There's also the constant k. So as homework, I want you guys to work out the solution to this. Okay. So it's like an exercise, I suppose. Sine, or it's probably also going to be cosine, and because both of those guys are probably solutions to this differential equation, their sum is also a solution. So one neat thing about differential equations or this course is that if you have a solution or a specific solution for a differential equation and you have another solution that's different from the first one, their combination is also a solution to the differential equation. Okay? Because what we can do is, well, we can plug them both in separately into the differential equations, and into the differential equation, and then it would yield the same answer. Okay, same answer. So how does this apply to our study? Well, if we use our g by t space again, so now we have our t again, and then our g, and then you can think of this actually as a pendulum. We can imagine or abstract or idealize the behavior for Femboy as something like a pendulum. And yeah, as we know from here in the pendulum, we know that the pendulum oscillates back and forth. It goes back and forth like this. And you guys know that oscillating movements are best described through waves. And waves are sine. Sine waves, cosine waves. So, yeah. It's oscillating. Since it's oscillating back and forth, it's best described by a pendulum. Wait for the noise to die down a bit. Structure noise. Okay. So, we can think of this as a behavior. So, we can think of this M as one part here, or one extreme, and then F or extreme. So it moves here, back and forth, the pendulum. So our behavior pendulum, I'd say. And then, so now, we can apply this, and of course model it, given our differential equation, which is theta. Double dot, is beta squared, theta equals 0. So we can model it using this. And our phase space, or our slope field for our differential equation, is something that goes like a spiral. So if I'll make a picture here again. It goes something like this. There, something goes like that. And I don't know if you guys can see it. It goes something like that. And any differential equation, like our usual phase spaces, would satisfy any differential equation that follows the flow, or actually function that follows the flow of this phase space, is a solution to the differential equation. And sine waves in the phase space, or input in the phase space, follows the flow here, where it circles all the way down to, well, oscillates slowly or smaller and smaller until it reaches 0. Okay? So that's actually a pretty neat thing, is that it eventually settles down to something, and it also is able to, well, model, I suppose, damped behavior and critically damped behavior. When we say critically damped, if it's, if it's damped, of course, it spirals inwards, right? But if we have normal behavior that continues on and on, they continue to be a gender fluid person until the end of their life, I suppose it'll just circle around like this. It just keeps circling in that phase space. If we damp the behavior or force it to, I guess, converge at a point, then I guess they would follow the flow, and they will, end up somewhere near 0 or somewhere in 0 or somewhere one of the two extremes. And if it's critically damped, we basically they spiral in faster. So critically damped is they spiral faster, or they go straight to the origin. And so let's check the time. 22 minutes. We still have time to discuss something else. It's nothing much actually in the way of the work. My sweat keeps dripping on the book and my notes, which is infuriating because it's hot here. I just have a haircut. Yeah. So you don't see so long hair on me right now. The behavior, Femboy Pendulum, the behavior operator, behavioral diffusion, conduction of confidence and down. Yeah. So I guess this lecture is going to be short like the other ones. It's not really going to be that long. Just 22 minutes or more. And then so the next one we're going to be discussing about the behavior operator. Which is something like I guess the Laplacian. It's just basically the Laplacian, and behavioral diffusion. So we're also gonna, I suppose we're gonna discuss also about the wave equation or the heat equation and its relation. And so the heat equation, if I'm gonna state it briefly here, is I believe it goes something like b squared f over dt squared is equal to minus alpha times the, or wait, no, it's just regular d, not d secondary. I guess correct me. Where in f here is a function of the temperature of a slab, and it's expressed in terms of x, y, and z. Say if you change the position of our point, we get some different temperature on the slab or whatever material we have. And this is a heat equation that governs, like, say, if one part is cold and one part's hot, and then we let time flow, it would sort of, I guess, stable out, and that's called diffusion after all. It's diffusion or heat transfer. And then this minus alpha is the heat transfer coefficient, and then this is basically just our Laplacian that describes the rate of change of moving a particle around the slab or the material. and then this is basically our change in time. So the rate of change of time. So I suppose the elapsing of time is equal to some constant times, well, the velocity of a particle moving through the slab. Okay. So yeah, that's the heat equation. We're probably gonna apply that in the next few lectures. So that's it for this lecture. I know it's short. It's not like the lectures in position theory. That course is pretty much, it's very dense actually, and it contains a lot of mathematics. And equally, I know that this course contains a lot of mathematics. But unlike position theory, here in regicalculus, we want to sort of stretch it out because differential equations are a very hard to grasp topic, especially for new students. And they're really freaking hard to solve, just so you know. And it doesn't mean that it's long or the video is long that we start expounding upon how to solve these guys. What we want you guys to actually do is, in your spare time or whenever you're doing your homework, figure out the techniques to solve these things. So what we focus on the course is the intuition behind solving the problems, and then in your spare time or in your homework or your, I suppose your assignments or your assessments, or if we have exams, that's where you guys are supposed to, you're expected to crunch the numbers in. While of course maintaining the intuition required to understand these things. So that's it for this lecture, and I'll see you guys in the next one.